Good morning, welcome to new lecture. Today I will solve new sample problems. If you remember, I was talking about this example. I will complete the solution of this example. We have three rods. Length of each one is L. Cross-sectional area is A, and Young modulus it is E. So LEA, LEA, and LEA. Angle between each rod is 120 degrees. So this system, as you see, it is kind of axis symmetric system. It is axis symmetric system. Coefficient of linear coefficient of expansion, it is alpha. We increase temperature in two rods, delta T. We want to find internal force in each rod. So problem statement says in the following structure, temperature changes in two members is equal to delta T. Determine the internal force in each member. State whether each member is in tension or compression. Assume thermal expansion coefficient is equal to alpha for all members. What we will do here? First, we will assume, for example, we are increasing temperature in these two rods, and intersection point, for example, point O, it is free to move. So we assume we don't have this third member. What will happen? If I increase the temperature, the length will increase in each rod. And we know how much the length will increase. The length will increase alpha delta T L alpha delta T L. So length of each member now it is L plus alpha delta T L and L plus alpha delta T L. So this is new length. So for compatibility reason, each rod should rotate respect to point, for example, A, B, C, point A and B. So if this rod rotating respect to the A, it will be similar to we drove arc with radius of L plus alpha delta T L and the center of A. That will be like tangent to the pathway. So again similar things here. So point O, intersection point, will move to point O prime. This is I show with delta O1. You see delta O1, if this angle is theta, this angle is theta 2, so it is 60 degrees. You see here, delta O1 cosine theta is equal to alpha delta TL. So delta O1 should be equal to alpha delta TL divided by cosine theta. Cosine 60 degree. Cosine 60 degree is 1 over 2. So this will be equal to alpha delta TL. So this point O will move down, and we know the magnitude. It is 2 alpha delta TL. Because in reality we have this member. This member will not allow this point move down freely. So it will apply restriction. It will apply reaction force. The reaction force is similar to the one force like F. The magnitude of that force F, it is unknown, but it is reaction force produced by third member. We assume this is unknown F. Unknown F will cause point O prime move a little bit up to this point. I show this movement with delta O2. Delta O2 will be equal to this force divided by stiffness of these two inclined members in vertical direction. The stiffness of each member will be EA over L cosine square theta, because this angle is theta. Because we have two of them and they move together, they are parallel, so 2 times of them. Cosine 60 again 1 over 2, cosine square will be 1 over 4. So if I simplify this, this will be 2EA over L times 1 over 4. From here, 1 over 4. From here, 2 will cancel with this 4, so we will have 2 here. This will be equal to 2FL over EA. Of course, it was 4FL over 2EA. They will cancel, so 2FL over EA. So, what is the final deformation of the point O? So first, because of temperature, point O will move down. We know how much it will move down. Then, because of the reaction in the third member, this member, reaction force, it is F. But that unknown F, we don't know the magnitude, will cause to move a little bit up. How much? It is 2FL over EA. So what is the final location? Final location will be delta O1 minus delta O2. That will be delta O, final deformation of this point. How much it will be? It will be finally equal to force in this member, which is unknown F, divided by stiffness of that member. The stiffness of that member in axial direction, it is EA over L. So if I substitute everything here, delta O1, it is 2 alpha delta TL minus delta O2, it is 2FL over EA is equal to, this will be FL divided by EA, FL divided by EA. If I take this to other side, I can write 2 alpha delta TL is equal to 3FL over EA. From here, I can find F. F will be 2 over 3 alpha delta T E A. And we have tension in these members or compression. It is clear this force in this member will be compression force, not tension. So this is compression, the reaction applies upward, so this is compression, this is compression. All member, we will have compression force equal to this F, and we find F from here because we have one equation, one unknown, I can find F. Let's look at another problem. Again, I have one axis symmetric system. Three rods. This angle is 45 degree. This angle is 45 degree. Young modulus, it is E, E, E. Length is L, L, L. Cross-sectional area for this member, it is A1. For these two members are A2. So A2, A2, A1. We have external force here. Magnitude, it is known value, we show it, P. We want to find A1 over A2 ratio so that internal force in these three members equal, they should be equal each other. So we will find A1 over A2 in a way to end up with equal internal force in each member. Let's see how we can do that. If I pull this down, what will happen if this is point, for example, A, B, C, and this is point O. Point O will move down, and because it is axis symmetric system, it will move down only. It will not go left or right, it will move down. So, if it moves down and it comes to the point O prime, this is delta, that will be delta. So we will have elongation in this member, and this member will be subjected to the compression force, so the length will decrease in these two members. F1 force in, I can show it like FOA, internal force in this member, will be equal to stiffness of that member, E A1 over L, times deformation delta. This delta, it is unknown. We assume it will deform like delta. But if this point will move down, delta, internal force in this member will be EA1 over L times delta, because axial stiffness for this member, it is EA1 over L. On the other hand, F2 in vertical direction component of this force in the vertical direction, or component of this force in vertical direction. Pay attention, internal force in these two members should be equal because it is symmetrical system. Component of this force in vertical direction, I show it, let's show FOB vertical will be stiffness of these two members, or stiffness of this member, not these two. Stiffness of this member, which is E A2L. In vertical direction, cosine square theta. Theta will be this theta, because this is 45 degrees. This angle again will be 45 degrees. So cosine square 45. This will be vertical component of the force. Pay attention, force here. Okay. We find vertical component FOBV. Vertical component will be stiffness of this member in deformation direction, in vertical direction, times deformation. So this is stiffness of that member in the deformation direction or in the vertical direction, or if this is x, this is y. In the y direction, stiffness of that member in y direction times total deformation. Because this angle is 45 degree, so what will be FOB? FOB cosine 45, you get to that triangle, FOB cosine 45 is equal FOB vertical. If I plug this here, I will have FOB cosine, let's see, everything is right. Yes, FOB cosine 45. Yeah, yes, it is right. FOB cosine 45 is equal to EA2 L cosine square 45 times delta. From here, FOB will be equal to EA2 over L cosine square 45 delta. Problem statement says internal force in these members should be equal, so FOA should be equal to FOB. FOA is EA1 over L delta should be equal to EA2 L cosine. This cosine 45 and this cosine 45, they will cancel each other, so this will be cosine 45, not cosine square. Initially it was cosine square, this cosine 45, this cosine 45 will cancel, so this is cosine 45. Cosine 45 degree times delta L, L, E, delta, delta, they will cancel each other. What we will have A1 is equal to A2 cosine 45. From here, A1 over A2 will be equal to cosine 45, which is equal to the square root of 2 divided by 2. So we find a ratio. Let's look at another problem. We have two rods. They are hanging under self-weight. Like this. Entire weight for this segment, it is W, length is L, E, A. Entire weight for top segment, top part, it is 2W, length is L, E is E, cross-sectional area is 2 times of this cross-sectional area, so 2A. A, B, C. We want to find delta C under self-weight. Delta C here will have 3 components. One will be deformation of this part, only, for example, part 2, part 1. Deformation of this part 2 under self-weight, we calculate that using integration. That deformation will be, if I show with delta 1, the delta 1 will represent deformation of part 2 under self-weight will be equal to entire weight times length divided by 2 EA. This I proved using integration. It will be W times L divided by 2 EA. That is the formation of part 2 only under self-weight. Delta 2 will be the formation of part 1 because of the weight from part 2. Because this weight of part 2, it behaves similar to external load at end. So this is segment 1. This load, entire load, W here, it is like external load at point B. So, if we have external load W at the end, what will be the formation? Will be external load times the length divided by EA of this part. EA of this part, it is 2EA. That is another component. The last component, delta 3, is the formation of this part, top part, under its own self-weight. Self-weight for that part, it is 2W times length divided by 2 times of E2A. So it will be 4EA. If we add these together, delta will be delta 1 plus delta 2 plus delta 3. We will find delta C. So delta C will be equal to WL over 2EA plus WL over 2EA plus, if we simplify this again, we have WL over 2EA. Finally, delta C will be 3WL over 2EA. So delta 1 is the formation of this part under its own self-weight. Delta 2 is the formation of top part under effect of weight for bottom part, this part. Delta 3 is the formation of top part under self-weight of top part. So if we add together, we will find delta C. Let's say solve one more problem. We have this system. It is one axial bar with different cross-sectional area. Length for this part, it is L. For this part, it is 2L, L and L. Again, for this part, it is L. I put name, for example, lowercase a, b, midpoint c, d, e. We have external axial load. One is P, like this. Another 2P, like this. Another 2P is here. Cross-sectional area it is 2A, 2A, and A. Young masses, it is E, E, E. We want to find the ratio of reaction at support A over reaction at support E. We want to find this ratio. In order to find that ratio, we should find reaction. But if you look at to here, what we have reaction A here, reaction E here. But if we add everything together, we can write summation of forces in horizontal direction is equal to 0. So it will be P plus 2P plus 2P minus reaction A minus reaction E is equal to 0. From here, reaction A plus reaction E will be equal to, this will be 4P, 5P. So if we take another side, 5P. But here we have one equation, two unknown. We cannot find reaction A and reaction E with this equation. In other words, this system is indeterminate system. So we cannot find reactions only using equilibrium equations. And we need compatibility equation. So what we should do? Assume we don't have this support. Assume we don't have this support. If we don't have that support, what will happen? In that case, if we don't have this support, this section will move from left to right. And that deformation, we assume it is delta. How much is that delta? That delta is summation of deformation for AB part, BC part, CD part, DE part. So it is summation of deformation AB plus deformation BC plus deformation CD plus deformation DE. Let's see what are magnitude of this deformation. From A, I am moving from left to right. From A to B, what is internal force in this segment, AB segment? This is free end. From A to B, any section, if I cut it, internal force is 0. So, delta AB is 0 because there is no effective force in this region. From B to C, any section, if I cut, internal force, it is P, and that will be equal to P times the length of this part, L, divided by EA, plus deformation for CD part. P we have here, 2P we have here. So internal force from C to D, it is P plus 2P, it is 3P. So it will be internal force 3P times length L divided by EA again, plus internal force in DE part will be, internal force in DE part will be P plus 2P plus 2P. It will be 5P times length for this part, D part L, divided by EA. EA for that, it is 2EA. This will be equal to 2EA. This will be 2PL. This will be 6PL, so 2PL plus 6PL plus 5PL. That will be equal to 13PL over 2EA. So deformation, total deformation, if we don't have support here, this section will move delta from left to right. That magnitude of delta, it is 13 PL over 2 EA. But in reality, because we have support here, this support will apply reaction. That reaction will move this section from right to left as much as delta. So first, if we don't have this section will move here, then because of this external reaction, like external load here, this will move back. So how much it will move back? Again, delta. This time, this delta is because of this reaction. Delta, because of that reaction, again, it is deformation of this part, and this part. Deformation of the AB part will be force here. It is reaction times length divided by 2EA plus deformation for this part, BC plus CD part, internal force from B to D, now it is reaction A times length 2L from here to here over EA plus internal force in D part will be reaction times length over 2EA. This will be equal to 2EA. That will be 4, 5, 6. So that will be, if I'm not wrong, should be, let's see. This will be reaction times length 2EA, reaction times 2L over EA, reaction times L over 2EA. So if we add together, it will be, this will be 2RAL plus, sorry, it will be RAL plus that 4RAL plus RAL. That will be equal to 2EA. This, if we add it, this will be 5, this is 6. 6 RAL. This will be equal to 3 RAL over EA. Now these two deformations should be equal because finally we have support here and deformation magnitude is 0. If we put these two equal, so from here we have 13 PL over 2EA is equal to 3 R and this A reaction at point A times L over EA. EA and EA, they will cancel each other, L and L. From here, reaction at A will be equal to 13 P over 6. If I plug this reaction now here, I can find reaction at point E. Reaction at point E, if I write here, reaction at E will be equal to 5P minus 13P over 6. That will be 6, 30, that will be 17P. So, that will be reaction at point E will be 17P over 6. If we divided these together, we will have 13 over 6P divided by 17 over 6p, p and p cancel, 6 and 6, it will be 13 over 70. This will be the ratio for this fraction. Thank you so much for watching this lecture. See you next session. Bye bye.